Imagine an industrial testing lab. Suspended from the ceiling are 4 metallic wires, each manufactured to the exact same length and thickness. We have 4 identical iron weights attached to the ends of these wires at the same time to see how each material reacts. This schematic maps the physical results. Look at the horizontal reference line. Even though starting dimensions and weights were identical, they haven't stretched equally. The aluminum wire has stretched downward significantly, but the steel wire, under the same load, its displacement is barely noticeable. The initial dimensions were the same, which means the difference lies in each material's specific molecular resistance to being pulled apart. To explain why steel holds firm while aluminum gives way, we need to quantify this resistance. Let's isolate a single wire to analyze the internal mechanics of a physical stretch. In this model, you can see the deforming force acting. The weight pulls directly downward, acting perpendicularly across the circular cross-sectional area of the cylinder. In physics, we define this relationship, the pulling force applied over a specific area, as tensile stress. As the stress is applied, the material yields. We measure this physical consequence by comparing the change in length against the wire's original, unstretched length. Dividing that change in length by the original length gives us a ratio known as longitudinal strain. For small deformations, these two concepts operate in lockstep. According to Hooke's law, the stress you apply to a material is strictly proportional to the strain that results. Force applied over an area, and the relative length the material changes. Stress and strain are the essential building blocks for quantifying how any solid object behaves. Because stress and strain are proportional, their ratio creates a constant value. This ratio serves as a mathematical signature for the material being tested. This governing constant is called Young's modulus, and we represent it with the letter Y. To make this useful for engineering, we expand the equation by substituting our physical components, force over area, divided by change in length over original length. Simplifying that fraction gives us the final formula. Young's modulus equals force times original length, divided by area times the change in length. Pay attention to the variables. Because the change in length is in the denominator, a tiny physical stretch results in a very high Y value. A high Young's modulus means you need an enormous amount of force to produce even a microscopic change in shape. By calculating this single number, we have a tool to predict exactly how much a material will resist deformation under load. Now we can apply these calculations back to the results of our initial lab test. This chart compares the specific Young's modulus values of our materials. Aluminum sits at 70 gigapascals. Steel reaches nearly 3 times higher at 200 gigapascals. The data explains the physical behavior. Steel's higher modulus value means it demands significantly more force to yield, which is why it resisted the weight while the aluminum wire stretched. This creates a common misunderstanding. In everyday conversation, elastic is often used to describe things that stretch easily, like a rubber band, but the scientific definition is different. Elasticity is a body's tendency to regain its original size and shape the moment the deforming force is removed. Because steel strongly resists deformation and requires significantly more force to stretch, it has a higher modulus of elasticity. By the laws of physics, this makes steel more elastic than the aluminum wire we saw earlier. This predictable resistance is vital for safety. It allows engineers to design steel bridges that flex slightly under the weight of a heavy truck, and then immediately return to their exact original shape once the load passes.